Hi everyone, welcome to Mathemly. Welcome back to our neural networks series. So far, we have explored why neural networks need layers and nonlinearity, and we have zoomed in on a single neuron to see how weights and biases shape its decision. Today, we put those pieces together and watch how data actually moves through an entire network in a process called forward propagation, the network's very first guess before any learning happens. To make this more concrete, let's follow a real-world example throughout the video, which will be predicting the price of a house based on features like size, number of bedrooms, and location. So, let's dive in. Forward propagation is simply how information flows through a neural network from the input layer through all the hidden layers and finally to the output layer. Think of it like a relay race. Each layer receives information, transforms it, and passes it forward to the next. The last layer crosses the finish line with a prediction. In our house price example, the input layer starts with the properties details: size in square feet, number of bedrooms, distance to the city center. These numbers travel through the network, where each neuron processes them using its weights and bias until the final output layer produces the predicted price, let's say $120,000. Let's take a closer look inside one layer of our network to see what is really happening. Each layer consists of multiple neurons, and every neuron performs the same basic operation we have already seen. It takes in several inputs, applies weights and a bias, and produces an output. So, as in our example, in the first layer, one neuron might focus on the size of the house, another on the number of bedrooms, and another on how far it is from the city. Each neuron calculates its weighted sum using the formula Z equals weight 1 times size plus weight 2 times bedrooms plus weight 3 times distance plus B. Here, the weights act like importance scores. A large positive weight for size means bigger houses push the output and therefore the predicted price is higher. A negative weight for distance means houses farther away from the city reduce the predicted price. The bias gives flexibility, allowing the neuron to make meaningful decisions even when all inputs are small or zero. Once the neuron has this combined value C, it doesn't just stop there. It passes that number through an activation function such as ReLU or sigmoid, which decides how much of that signal should move forward. The activation acts like a filter. Small or negative signals might be reduced or cut off, while stronger signals pass through more clearly. This step ensures that the neuron doesn't just react linearly to inputs, but introduces the flexibility needed to capture complex relationships in the data. Finally, the outputs from all neurons in this layer become the inputs for the next layer, where the same process repeats. With every layer, the network transforms the data slightly, step by step, until it's shaped enough to make an accurate final prediction. So, inside a single layer, what looks like a bunch of numbers multiplying and adding is actually a small team of neurons, each focusing on a different aspect of the problem, working together to extract richer and more abstract patterns from the data. As the data moves through multiple layers, each one learns to recognize more abstract features. In the early layers, neurons might focus on simple patterns like bigger houses usually cost more. Deeper layers might start combining those ideas. For example, large houses near the city are especially expensive. By the time the signal reaches the output layer, the network has woven all these mini insights together into a single informed prediction. This is what makes deep learning powerful, by stacking layers and allowing the network to understand patterns that no single equation could capture. Here is the interesting part. Before training, all the weights and biases in the network are random. That means the very first time we feed in our house data, the prediction it gives maybe $640,000 or $120,000, is completely arbitrary. This first result is what we call the network's first guess. It might be wildly wrong, but it is a crucial starting point. Once the network compares this prediction to the actual house price, it can measure how far off it was and adjust the weights using backpropagation, which we will cover in the next video. For now, forward propagation is just about pushing data forward to get that first untrained prediction. So, here's another real-world example of this concept. Imagine you're learning to bake a cake for the first time. You mix the ingredients, bake it, and taste it. That first bite tells you what to change, maybe less sugar or more baking powder, but you had to make that first cake to learn what's wrong. Forward propagation works the same way. It's the network's first taste of its initial attempt to understand the relationship between inputs and outputs before any fine-tuning happens. To sum up, forward propagation is the network's first pass of data from input to output. Each neuron computes its weighted sum, applies its activation, and passes the result forward until the final layer makes a prediction. This first guess is the starting point for learning, which we will refine using backpropagation in the next video. If you found this video helpful, don't forget to like, share, and subscribe to Mathemly for more data science tutorials. Comment below with what you would like to learn next. Thank you for watching and see you next time.